Okay, hello everyone. Welcome to the last plenary talk of IROS 2014. It is my enormous pleasure to introduce Andrew Davison. Andrew worked on his PhD at Oxford. He actually developed the first visual SLAM system that really worked. And because the subject of SLAM was in its infancy, or maybe its early adolescence, he did not abandon the subject after his PhD like is frequently done or even advised, but he kept on trying to do the things that were yet to be done and improved in the subject. SLAM turned out to be a core problem in mobile robotics, as John Leonard likes to say, whenever you have a sensor that is moving, you have a SLAM problem. I met Andy at the first workshops on SLAM at ICRA, and like many people, I was deeply impressed by the casual way in which he demonstrated his mono-SLAM system. Just a CCD camera, a cable, and a laptop. And it worked. Um, from that mono-SLAM prototype, many things have resulted. One example is Google's Tango project. And it has been so successful that it attracted the attention of a company like Dyson that recently invested $8 million in the Dyson Robotics Lab at Imperial College in London. Andrew is now robot vision professor at Imperial College and of course is director of that lab. I think that that was a very smart investment, and I'm sure that we are going to see wonderful things come out of there. Please join me in welcoming Imperial College Robot Vision Professor Andrew Davison.
Well, it's a real honor to be here, and thank you very much, Jose, for the introduction. So, obviously, we've already had one excellent keynote on vision from Peter Cook, so I won't be going quite as far back as he did. I'll probably go maybe about 20 years back and show you a little bit of the history of this area of visual SLAM and a bit of a view of how I think things are going, as well as a couple of the most interesting things that we've done recently, but really keeping focused within the area of visual SLAM, because vision is a huge area. So I call my group the Robot Vision Group, and actually, you know, it is primarily a computer vision group, but we are very much specialized in what I call robot vision, which is not necessarily just vision for robots. I think for me, it's vision for the real world, normally in a real-time loop, and for a purpose. And it's turned out that that's been quite useful for other applications that you might not think of as robotics. So I've been working in this area since my PhD, started just 20 years ago next month, actually. And what's been really exciting in the last couple of years in particular is to see how this area has really matured, and it's really starting to become practical for low-cost consumer devices. So there's a couple of examples here. The Dyson 360i that I have been actually working on as a consultant for nearly 10 years. I'll show you a little bit more about that later, but it's very exciting that it's finally been announced. Another very interesting project, which I wasn't involved with, but I find really interesting is Google Project Tango, which is all about basically trying to put visual SLAM into a phone or a tablet format device. So they've specially engineered the hardware and got all the best algorithms together to really try and make it work, and it's very interesting. So, you know, I've worked in this area of visual SLAM. I've always been most interested in using vision to localize and map within a fairly small building block area. So yes, you can try and make SLAM maps of huge areas, cities, and there's been a lot of really interesting work on that. But for me, it always comes back to, can you make a really great map of that little local area around you, a few square meters, your camera's going to be moving around like this, and you want to do something sensible there. And I think it's really enabling, and we keep coming back and trying to make that better and better. And those, of course, can be building blocks of much bigger maps. And I think a trend that I've seen is not, you know, I've never been one of these people that said SLAM is finished, like people started to say at least 10 years ago. I think SLAM as an area has been gradually evolving towards something which we can now think of as general real-time spatial perception. And hopefully some of the things I'll show you will give you an idea of what I mean by that. So this is the first robot that I worked with. So back in the mid-90s, so I was doing my PhD at the University of Oxford with Professor David Murray, and we had this system, which was a robot, a three-wheeled robot with odometry and a stereo active head. So this is a mechanized camera platform with two cameras. And we basically thought, well, can we actually make a persistent map of a space using this system? So what it basically does is the head moves around, and at any one time, it's looking at one feature. So in the center of the field of view, you'll see that it keeps coming back to particular landmarks of interest that it's picked out, it tracks them, it makes measurements, and then it feeds all of that into an estimation engine. So the output of that looks something like this. So these are maps built by this system. So here's an estimated trajectory of the robot, and then these are estimated feature positions. And you'll see that each of these features has a ellipse around it, which represents uncertainty. So some of these are still quite big uncertainty. They're far away. They haven't been measured very often. Some of them are close to the robot. Many measurements. We have really good quality estimates. But what this system basically embodied and was actually really forced to do was a kind of closed loop predict, measure, update procedure. So actually with this robot, we could only measure one feature at a time. So we were forced to always make decisions about which feature we were going to measure next, because we actually had to move the robot head to look at those features. And then as we went around and made these measurements, so we selected which feature to measure, made a measurement, and then fed that into a sequential probabilistic filter. So as the robot moved, it looked like this. So whenever it moved around, we made some prediction of where it had moved using odometry. We updated its estimate of its position, uncertainty in its position increased, and then we observed features in the scene. And as you move around and make repeated measurements of features, you'll see that this uncertainty in all of these things gradually evolves, and in the case of the features, it monotonically reduces. So as you move around and make lots of measurements of features from different landmarks, you get more and more certain about their positions. And at the same time, you have an evolving estimate of where the robot is with respect to that. So how you actually implement that in a computer, we were using an extended Kalman filter, which effectively does first-order error propagation. So it assumes that that uncertainty is a joint Gaussian across all the variables that you're interested in, and it sequentially updates it over time in the form of a state vector and a covariance matrix, which is basically representing uncertainty, the shape of this joint Gaussian across a lot of parameters, and updated in a purely incremental way. So that was very, nice system. As Jose said, I think one of the very first visual SLAM systems that actually worked in real time and could do small loop closure and so on. But I thought, well, it's hard to actually get people interested in this because hardly anyone can re-implement this. It's a complicated system. There's this very specialized hardware and so on. So can we do it with something much simpler? And in particular, can we do it just with a single webcam attached to a computer with nothing else? So getting this to work required solving quite a lot of problems compared to the previous system. So we had no odometry. We had general 3D motion. We wanted to track relatively fast motion, and we only had one camera. So we had no immediate way to triangulate and measure depth. So let me show you a bit about how that system works. And maybe I can explain a little bit how we overcame those challenges. So this shows you the kind of setup. So as I said, a single webcam, no prior knowledge, well, a tiny bit of prior knowledge about the scene. You'll see there's a special kind of marker on the wall that we point the camera at to initialize. But apart from that, nothing else. Reasonably kind of dynamic motion. So this is the camera's eye view of the world, and you'll see that the main thing that we're doing is detecting and tracking salient point features. So very much in the spirit of what we were doing with the previous robot, we're finding interest points which are high contrast things in the scene which can easily be tracked across multiple images. So an interesting thing about this system, and one of the ways that we made it fast, was what we called active feature search. So this was, again, very much inherited from the previous robot, which said that as each new frame came in, I'm not in active control of where the camera points to, but I am in active control of where I focus my processing resources. So those ellipses that you saw were actually search regions generated by predictions from the Kalman filter, and we would only make feature searches within those small regions. And that was one of the main things that made this system efficient. So here's the actual output of the system. So how to deal with this problem that we only have one camera. So that actually means you need to do something rather special when you initialize features. So you'll see that when we first add new features, a line appears in the 3D map. And then after we've made enough measurements, we turn that line into an ellipsoid. So we have a problem when we first see features that we don't have any initial estimate of their depth. We only know their direction. But it turns out that using a special parameterization, we can, over some period of small motion of the camera, get enough of a good triangulation of its depth to then initialize a Gaussian estimate of its position. And we did that initially with a particle filter-based method, and then later on we developed a method called inverse depth features, which turned out to be even better. So some of the things that we learned from this system was that good things happen if we stay within a high real-time frame rate. So Monoslam always worked at 30 hertz. And that's interesting compared to a lot of systems, because actually it wouldn't work at any frame rate lower than that. Because if you turn the frame rate down, if you tried to apply it to a 15 hertz camera, actually there's too much gap between one frame and the next, and the predictions are too uncertain. You have to search big regions to find the features, and everything kind of breaks down. So by keeping that frame rate high, keeping predictions good, you can keep the measurements efficient and robust. And that kind of made the whole thing work. So, one way of talking about that is saying we had a very tightly coupled front end and back end. So often in SLAM, people talk about the front end, which is the kind of visual measurement feature matching part, and the back end, which is the estimation engine, and discuss how much those things can be separated. And there have been many good systems where they have been completely separated. But Monoslam was a system that kept those things tightly coupled, and for me that's an interesting way to go, which I think still has a lot of currency, as I'll show you later. Okay, so I just want to show you this briefly, and I apologize for the rather commercial video here, but this is the video released by Davison of the new 360i robot. So this is a robot which navigates and by doing visual SLAM, basically. So it has an omnidirectional camera on the top. So this is the 360 in the name. So this gives it a wide strip across the whole field of view. So here you can see it. And here you can see, visualized here, we are actually tracking features. And in very much the same way as Monoslam, each of those measurements is harvested and then fed into an incrementally, probabilistically updated estimate of where the robot is and where the features are. So of course the robot, being a Davison product, has the dual cyclone cleaning system, and hopefully will do a very good job of cleaning the floor. But because it has quite a powerful cleaning system, it was very important for it to be properly localized. So it needs to really be sure about where it's been, where it hasn't been, so that it can clean in an efficient way and make sure that it's not repeating work that's unnecessary. So it also has an app that you can use to schedule it, but that's enough about that. Okay, so I've spoken about work up to this Monoslam system, and that was really 2003 we had that system working, and we did a lot of live demos in different places, and I think it's had quite a nice impact. But since that time, we've seen massive progress in visual SLAM, and one of the main aspects in that, which should never ever be disregarded, is how important the rise in computer power has been. So computer vision benefits from increased computational capacity, probably more than anything else, because it's a very, very data-intense activity, computer vision. And I think, a major trend that I have seen is as computer power has risen, we're able to take more and more of the developments that are always going on in the computer vision field and bring them into this real-time domain that we're interested in robot vision. So, if you go to a computer vision conference, you'll see, most of the work is very much offline stuff. They're algorithms that take hours or days to run. But, there are algorithms that were taking hours or days to run back in the 90s, or maybe not days, but definitely hours, which are actually now pretty much working in real time. So here are a few examples of increasingly computationally expensive computer vision algorithms that we've been able to bring into play in real-time robot vision thanks to rising computer power. So one of those is bundle adjustment, which I'll talk about in a second. Iterative whole image dense alignment for tracking, dense multi-view stereo matching and reconstruction, and dense machine learning-based scene segmentation and labeling. So these are all certainly things that, when I was working on SLAM in the 90s and even early 2000s, I didn't pay much attention to, because I thought, well, these are not useful to me at the moment. But it's turned out that they now are, and surely there are much more of those things out there still. So to talk about a few of those, I've borrowed a visualization here from Frank Delert. I hope he doesn't mind. But in the kind of mid-2000s, I think there was really good work around the world on understanding the general character of the SLAM problem, and realizing that this question of having a body moving through the world with outward-looking sensors and repeatedly identifying and tracking a number of features in the world has very common structure. And a very nice way of visualizing this is a factor graph, where here you've got nodes here for each point in time where you want to estimate the position of your robot or moving camera, and then you've got nodes here representing the landmarks in the world that it observes. And then each one of these lines here with a little dot is called a factor, and that's basically a measurement from one robot pose of one landmark. And this representation makes it easy to see that an alternative way of solving SLAM rather than an incremental Kalman filter is as a batch nonlinear optimization. And it turns out that's exactly what has been known in computer vision for a long time as bundle adjustment, or at least the vision only case of that problem, I would say, is called bundle adjustment. When you bring in other sensors, it's slightly more general. So basically, this leads you to a nonlinear least squares optimization problem, where you get one term in this least squares sum for each of these factors, which is a measurement. And the least squares aspect of this comes if we basically assume Gaussian measurement models on each one of these measurements here. So when you take the minus log of an exponential function, you get a square term. So maximizing probability is equivalent to minimizing energy, which is minus log probability. So one of the first systems which really successfully used bundle adjustment in the loop of SLAM was called PTAM, a very influential system by Klein and Murray from Oxford in 2007. So again, rising computer power means we can do more, but what you can't do is just take every image you've ever taken and continually bundle adjust everything. So consider that graph. Every time you move to a new position and take more measurements, the graph gets bigger and bigger and bigger. And what you can't do is on every new frame at 30 frames per second, crunch that whole thing, which is getting bigger and bigger all the time, and solve for it. So people have come up with very nice kind of management strategies for saying, I'm going to use that nonlinear optimization, but I'm not going to try and solve the whole thing at every step. And what PTAM did, so PTAM really got my attention because they were solving exactly the same problem that I had been with MonoSLAM. It was a small building block of a map of a few meters cubed, but they showed that using a careful optimization strategy, they could make maps with much more features. So you see they're tracking hundreds of features per frame, and they're building a map with thousands of features in a few meters cubed, whereas MonoSLAM tracked 10 features per frame and made a map of maybe 100 features. And doing that gives you basically much more accuracy in your position tracking. So the particular thing that PTAM did was this idea of keyframes. So rather than keeping all of the data, you just keep a selection of keyframes, so previous frames from your history of motion, but you distribute them in a nice spatial way. So if my camera's here and it's been near here before, I will have a keyframe near to this position, so I don't add another one. But once the camera explores enough away from places it's been before, you add more keyframes. And that means you can span a reasonable volume of operation with a few tens of keyframes, and that's what keeps the bundle adjustment thing running fast enough. So we and various others, extended that basic approach. Here's something called this is called double window optimization for SLAM. So if I show you this bit of the video, which is a simulation, this is a system which allows basically a PTAM-like method to scale to much larger areas, but retaining real-time operation. So, PTAM will still grind to a halt if that number of keyframes gets too big. So, once it gets up towards 100, even the bundle adjustment can't keep up. But in this system, we kind of have a double layer approach where we use full bundle adjustment in the region of frames which are close to the current camera position, and then we use a more approximate type of pose graph optimization on the larger scale. And that means we can get, really large scale, real-time visual SLAM results like this, where you can close big loops. Okay, so talked about bundle adjustment. So now let's talk about some of the other aspects I said where more computer power is now enabling us to do more in real time. And in particular, what's really been significant in the last 5+ years, maybe 7 years, is the rise of general purpose GPU processing power. So these are the graphics cards from NVIDIA and other companies, which are obviously initially designed for gaming. They're designed for high graphics performance, but people started to use those graphics cards as general purpose processors, initially by hijacking the graphics API and pretending that vision computations were graphics computations. But then the companies started to support that with specific programming languages for general purpose programming. So NVIDIA's CUDA, for instance, is what we've used a lot. So that's significant when you look at curves like these. So this is gigaflops against year for commodity processors, and down here we have the CPUs, basically. So here starting to get a little bit more parallel, but this is nothing compared to what's going on in GPUs, where easily the most powerful processor in a typical gaming related PC now is the graphics card. Now, of course, that is very, very processor, very, very powerful, but it's a massively parallel type of computation. So that means you have to have the right algorithms to be able to take advantage of that. So the other things that I'm going to show you now are all those sorts of massively parallelizable algorithms. And I think, for me, what GPUs really enable you to do in real-time vision is the type of operations that do something at every pixel on every frame. So this starts to move us away from the world where we have to first extract point features and only consider those. Here, we're moving towards methods that do things with every pixel. So realizing that, we started to get interested in live, dense reconstruction. So there were results like these around in about 2007. So this is from TU Graz in Austria, showing real-time, dense optical flow running on the GPU. So this is basically from frame to frame, doing dense matching. So I want to find out where every pixel in this image goes in the next frame of video. So it's basically trying to find correspondences for every pixel in another image. And that can be used for the general optical flow problem, but it's also exactly what you need if you want to do dense reconstruction. So if you have a number of images, so in the previous kind of monoslam or PTAM stuff I showed you, we would extract points in each one of those features. We would match the points up, and then essentially by probabilistically triangulating all of those points, we can work out the depth of all those points. In these methods, we want to do that not just for special points, but for every single pixel of the images. So we basically, for every pixel in this image, I need to find correspondences in all these other images so that I can triangulate. And the result of that is I get a depth map. So the way that these algorithms work is to basically bring in a little bit of background knowledge that says, well, actually, the world is not a random point cloud. The world tends to consist of coherent, continuous surfaces. So therefore, the depth of nearby pixels or the flow of nearby pixels is likely to be similar. So that is characterized by energy functions like this that balance a photoconsistency term with a smoothness term. So this is a term that says penalize any solution where the sum of gradients is too big. So this particular one is called a total variation energy term. So these solutions allow you to match those parts of the image where we wouldn't have found features, because actually there's hardly any texture. So if you consider a pixel in the middle of a table or something like that, it just looks quite bare. There isn't much to tell us in the other image where that matches to. But if we take the support of all the other pixels around and search for a solution which is globally smooth in some sense, then we can actually get pretty good matching solutions even for those textureless regions. So, the thing that guys like Thomas Pock from Gratz showed was these sort of algorithms, which again had previously been very offline optimization algorithms, can be run in the right way or on a GPU in a massively parallel way and bring you towards real-time performance. So to show you the first thing we did with that, this is a system called Live Dense Reconstruction, which was mainly by Richard Newcomb in my lab. So we're moving a camera over a scene, we're gathering little bundles of frames, and then we're sending them off to this dense matching component, and pop, 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 we're generating little dense depth maps that look something like this, which we can then stitch together into a whole complete scene reconstruction. So again, this is just from a single camera with no other sensing. We're able to construct, this level of a model of a scene. So another thing that we can do with GPU processing power is dense tracking. So that was dense reconstruction. But once you've actually reconstructed a scene, and we basically have a texture mapped model of the scene, which is a continuous surface, we have a new way of tracking the camera, which is instead of by matching point features, we can basically align whole images or scenes together. So here we're showing that if we slide two images from slightly different viewpoints, this is looking down a floor, over each other, we reach a point where the difference between those images at every pixel, the sum of all those differences adds up to something minimal. So we know when we've slid two things over the right way, when we subtract all the overlapping pixels and add all those differences up and get to a minimum. So that's in 2D. One of the things we did in 2D was a visual odometry system based on a downward-looking parking camera from a car, where we're looking down a fairly textureless road, but by aligning pairs of images using dense alignment, we can actually track the motion of the car very effectively. But even more interesting is that you can do this in 3D. So essentially, if we've got a new image of a scene and we have a textured 3D model of a scene, what we want to do is to find, what is the estimated position of the camera such that when I render the scene from that position, the image that I get looks pixel-wise as close as possible to the image I've actually got. So this is called, this is another classical vision algorithm, Lucas Canade alignment in 2.5D. And we brought this into our dense reconstruction system in the algorithm called DTAM. So here the first step is similar to what I just showed you. We move the camera in and around and basically paint in a 3D dense textured model of the scene. But then what we do is we turn off our point feature tracking system and we track by this whole image alignment against the dense model. So there's our dense model. Now we're going to show you dense tracking. So basically, as we're moving the camera around on every frame at 30 frames per second, we're aligning that whole dense model against our image. So here we have a head-to-head comparison between DTAM, which is our dense tracker, and PTAM, which is a very good point-based tracker. And we're showing here the quality of tracking by doing some augmented reality. So we've put this virtual car into the scene. So basically, on every frame, we're taking our estimated position of the camera, and say render the car as if from that position on top of the real image. And if the tracking is right, the car should look like it's really stuck to the scene. So we show that we can track better than PTAM, and even in this really surprising situation where we deliberately defocus the camera and show that we can still get pretty good tracking with our dense method, because we are accessing all of the information in the image. Even though feature points disappear, we're getting very good tracking. Yeah, so the final thing that I'll talk about in terms of computer power enabling us to do more is something that I think probably lots of people here are working on, but is using machine learning type methods to basically start to try and label up scenes and get some initial idea of semantic meaning. So if you can train classifiers to look at little local areas of an image or of a depth image, and associate that appearance with a type of category of object or structure, then you can apply those things across whole images and start to try and label up identities of what is what in an image. This is a chair, this is a piece of furniture. So you can do that in just a raw way, or you can then apply regularization, which is the same sort of smoothness assumption that I talked about in dense reconstruction, to give much smoother solutions like this. And again, this is something which is generally very, very parallelizable and works well on a GPU. But something I'd like to come back to is I think a trend that I've observed recently, that brute force processing has allowed us to do so much more, but still, when we want to make systems that really work well and are very robust, I think we're seeing a bit of a return of filtering methods. So by filtering, I mean incrementally and probabilistically updating a joint world model. So every new piece of data is treated separately and fused probabilistically into a model. So as opposed to kind of applying a dense or a sort of brute force pipeline. So this is a much more loopy way of doing things, where we've got our persistent world model. We use that to help us do the measurements, because we make predictions that allow us to do efficient measurement, and then we keep the loop kind of closed in a tight way. So the way Project Tango works. So again, as I say, I wasn't involved in that, but my understanding it is basically a tight visual inertial integration based on a Kalman filter type method. So it's basically a monocular camera with high quality inertial integration. That's what gives you the high quality pose in Tango. Another really interesting system that I didn't work on, which has just come out in the last year or two, is LSD SLAM is the amusing acronym, but it stands for large scale semi-dense SLAM. So it's kind of a middle ground in between a point feature based system and a dense system. So it tries to reconstruct not every pixel, but all the kind of pixels where there's some interesting image gradient, and they're not necessarily just feature points. So this system also works, by per surface element, it's doing basically incremental fusion using something like a mini Kalman filter. So another system which I did work on is Connect Fusion, and this also it actually works using sign distance function fusion, but it's also something you can interpret as a filter, so incrementally fusing measurements. And I think there's something particularly interesting about these two, that if you consider them as filters, actually the way they work is something that all my SLAM background says shouldn't work. It should be completely wrong, because instead of considering that SLAM problem as a joint estimation problem, where you're always considering the covariance between all the features and your robot position, you basically have separate filters estimating the position of each surface element, and somehow it still works, at least on a small scale. And I think there's something interesting about how the weight of data in these systems is just so much greater than anything we've had before. So instead of 10 features, in Connect Fusion, we're making 300,000 depth measurements at every step. Somehow using your processing power just to feast on all that data is better than feasting on not very much data and then spending loads of processing power worrying about what your uncertainty is. So that's something I still feel like I want to study more. So just to talk a little bit more about Connect Fusion. So you probably know about this, and it's really great to see a lot of papers in this conference that are building on Connect Fusion. So this was actually work that happened when Richard Newcomb, who was the student who developed the dense single camera systems I showed you, did an internship at Microsoft Research, and he got his hands on the Kinect camera pretty much before anyone else. And he'd done all this really hard work to try and get depth maps out of images, and now here was this sensor that threw depth maps at him at 30 frames per second. And so he really got to think about this problem of, when I've got lots of overlapping depth maps, what should I do? And his solution was to basically fuse those incrementally into a global model using this volumetric sign distance function representation. And then what was really, that wasn't a novel algorithm. That's a classical thing to fuse into a sign distance function. I mean, novel to get it working fast in real time on a GPU. But what was really interesting was he closed the loop by then tracking against the dense model. So all the tracking was always done by raycasting the current best dense model and doing ICP between that and the live image. So just to show you a little bit about what this dense sign distance function looks like, but you can interpret the way that averaging sign distance functions, which is what the process is pretty much equivalent to something like a Kalman filter running on each surface element, which is very interesting. And after he came back to Imperial, he did something really even more astounding, which was, I think, put the single camera depth map estimation together with the Kinect Fusion style dense fusion and show these kind of results with a single camera, where you can see amazing detail that we're picking out. Okay, I need to move on, but I'd like to talk briefly to finish the talk about two recent systems that we've worked on that I think are using this idea of a closed loop system to full advantage to do something quite new. So the first one is called SLAM++, or SLAM at the level of objects. So this is a system which doesn't do dense reconstruction, but it aims to build a dense map, but in scenes where we have a good prior knowledge of the sort of objects that we expect to find. I think it'll be best to show the video. So here the setup is again a handheld depth camera and a prior database of objects. So we're in a scene, something like this common room, where actually there are loads of similar things here. So in fact, there's a load of identical chairs of two different types. There's a load of identical tables of two different types. We have prior 3D models of the shapes of those objects. We've scanned them with Kinect Fusion. So what we do in this system is we don't reconstruct everything from scratch and then try and label it with object identities. Instead, we go straight in with an object detector and try and detect instances of those objects that we know about. And then we directly build a SLAM graph of where those objects are. So it's kind of like each one of those objects, like a chair, is a super feature. And then there's the SLAM kind of back end of this is something that's very much like a feature-based SLAM system. What we aim to build is a graph of where these objects are in the scene. But because we're doing it in this incremental way of getting the features of the objects as soon as we can, we get very nice properties like active search, which for me is something that kind of brings me back a bit to the sort of things we were doing in MonoSLAM. So this is saying that at any point in time, I know about a certain set of objects in the scene. So I don't need to detect those again. I don't need to reconstruct them. I've got a model. I'll just track it using ICP. And then I'll figure out which are the parts of the scene that I've successfully been able to track and which are the parts that I don't yet understand. And then I should try and find new objects only in these kind of white regions here that I don't yet understand. So our object detector, it's a GPU implemented method which kind of searches for interesting pairs of points which correspond to objects that we've learned about. And we basically need to sample a lot of random points in our depth image and see if we can vote for the identities of objects. But you'll see that we only need to sample red points here in the regions that we don't yet understand with our object models. So this means we have a very focused sort of image processing, which is trying to find new objects. So a new aspect of this system, which we've just published, and in fact not yet fully integrated, but it really should be, is yes, we can deal with objects for which we have prior models. That would deal with a certain number of pixels in the scene, but actually in a lot of scenes, something that you should really do is notice that there's a lot of large planar areas. Let's do something to efficiently map those. So this is a system called dense planar SLAM, where again, straight away on every frame, we're trying to detect planar regions. So we have frame by frame plane detection, and then we're taking all of those detected plane estimates and fusing them into coherent estimates of where the large planar regions are. So here you'll see the frame-by-frame estimates, and they're kind of noisy because they're just running on the pure Kinect images. But here we're kind of fusing those into coherent models where each of these planar regions is it's a plane, a parameterization, plus a kind of occupancy map telling us what do we think is the occupied area. And then we can have a kind of hybrid system where we have the planar regions, but we also have some non-planar stuff which we represent with non-parametric voxels. So, stairs, for instance, are very nicely coped with by this system. I mean, this would be a holy grail of indoor robotics, right, to have something that worked well on stairs. But it looks like we might be able to make nice maps with this system. And it turns out there's also very nice augmented reality things that you can do with this. So this is a kind of non-robotics application, but we've hooked this up with an Oculus Rift, and show that once you've detected planar surfaces, something nice you can do is use those planar regions to display information in a very nice way. So you can put your Facebook wall on a real wall, and that's probably nicer than having it hanging up, in front of the real information. Or here we show that you can change the color of the carpet if you want to do that. But you'll see the quality of registration and tracking is very nice. Okay, the final new system I'd like to talk about is some work we've been doing with these new types of cameras called event cameras, and I know that there are several people here who are already working with these, and this is very exciting. So these are these new neuromorphically designed cameras. They're meant to be like silicon retinas. They don't capture full-frame images. Instead, each pixel is asynchronously and independently trying to detect brightness changes, and the output from the camera is a stream of events of pixels telling you that they got brighter or darker and telling you exactly when that happened. So we've built a system that's starting to move towards doing SLAM with these cameras. So it's not yet 3D SLAM, it's a kind of pure rotation SLAM that tries to build mosaics. So you hold a camera up, you rotate it left and right, and the goal is to track the rotational motion of the camera while building a persistent mosaic. And we've shown that a SLAM approach here of kind of jointly estimating the motion of the camera and the shape of the scene allows you to progress on what otherwise seemed very difficult. I mean, it was initially, we didn't really know where to start of how to actually estimate things from this type of camera. So these are some of the results that we just published at BMVC. So here's the setup, handheld camera, basically pure rotation motion, and here are the events that it captures. But then the output is we're actually able to track the rotational motion of the camera and reconstruct the intensities in the real scene. So I think this is the first time people have seen, intensity type images coming out of an event camera. So the way that works is we are, so I'll just show you a couple more examples before I quickly show you how it works. So quite large scale rotation here, so building a big panorama. He's working on some different scenes indoors and outdoors. So intensity mosaics coming out of an event camera. So to just very, very briefly show you how that works. So first of all, we have a tracking filter, and this is currently based on a particle filter. So at any point in time, we have some estimate of where the field of view of the camera is with respect to a mosaic that we're incrementally trying to build. Now we receive an event from a certain pixel in our event camera. So for instance, this pixel reports that it's getting brighter. And the question is, which one of our current hypotheses of where the camera is with respect to the mosaic is true? So basically, we evaluate a likelihood for each one of these hypotheses that says, is this change in brightness consistent with this motion over the mosaic? And we get different likelihoods, and in the standard particle filter way, we resample and we get an updated estimate. So every little event is pushing our estimate a tiny little bit of where the camera is with respect to the scene. But it's doing this at sort of, almost microsecond-like intervals. So we've just moved far away from this big blind gap in between images that we have with standard frame cameras. So the other aspect is then how do we estimate the mosaic of the scene? This happens in two ways. So we have to estimate, first of all, a gradient map. So this is visualized here with these colors. So for every pixel in a high resolution mosaic of the scene, we're trying to estimate its gradient. And the basic way we do that is whenever we receive an event, we are getting some component about some estimate of the component of the gradient in the direction that we're currently moving in. So we have a 2x2 ellipse, a Kalman filter, estimating the gradient at each pixel. And every time we receive an event, depending on the motion of the camera, we squash down our uncertainty along that dimension. And then the final step is you can take a gradient map and update it to an intensity map. And this is basically a procedure of integration. So in 1D, it's clear that if you get a signal and differentiate it, you get this. You can integrate it back up and get that. There's a 2D equivalent of that, very well known in computer vision, called Poisson reconstruction. And that's the thing that enables us to go from the gradient map back up to a full intensity mosaic. So just to finish, I'd like to say that, computer vision's really going places in robotics. I think that the future of mobile vision has got to really think about how processors interact with algorithms. One of the projects I'm interested in is it's called the Pamela project in Manchester, where we're really thinking about how this multi-core landscape interacts with computer vision algorithms. There's very interesting things going on. For instance, a company in Ireland called Movidius developing custom low-power vision chips with really surprising performance, but within the sort of power envelopes that start to seem feasible for mobile devices. So we're going to work on that kind of thing. In the Dyson Robotics Lab in particular, we're thinking about what are the future vision-enabled technologies that are going to give us new types of robot products for the home. We're going to start looking at manipulation, where I'll be seeking the advice of lots of people in this room, because I'm really a beginner at that kind of problem. But we like to think that this kind of closed loop, predict, manipulate, measure, update type of approach with really high quality vision might enable us to do new things there. Thank you.
Thank you, Andy. I told you that great things were coming, and we just saw them. I think there's time for only one quick question.
Will the event-based cameras work when the scene is moving? Like currently the scene was static, but like creating like images using event-based cameras, will it work even when there is a dynamic scene?
I'm sorry, I didn't hear you very well. Was the question about moving objects?
So you showed like using the event-based cameras that you can reconstruct the scene, right? But the scene was static.
Mm-hmm.
So will the reconstruction of the image work using event-based cameras even when the scene has dynamic things like moving people?
So right now, certainly that algorithm is designed for static scenes, and that's built into it as it is in most SLAM systems. But I think there should be great potential to also track independently moving objects with an event camera, because you can really see tiny amounts of motion once you're measuring things at that rate. But we need new algorithms, as we do for everything with an event camera. I think there's 1 minute left on the clock, is there?
Yeah, maybe another quick question?
Thank you, Andrew, because your talk on SLAM showed something. SLAM started with robotics and moved to vision. And usually we see things coming the other way around. We use things coming up from vision. And this is a great lesson. So my question is about the foundational issues. When people say SLAM is a soft problem, probably they think that the basic algorithm are well known and that's it, we solved the problem in theory. Could you comment on the foundational issues if there are things which is quite open yet? Thank you.
Yeah, I mean, of course, in the end, it all comes back to Bayesian estimation, and Bayesian estimation is solved, and what to do with uncertain data, I think, is well understood. But for me, I've always been most interested in the kind of front-end part of how do you actually get those good enough measurements to feed into estimation, and for me, there's still a lot of open problems there, and I think, yeah, depending on a certain sensor and a certain setup, so for instance 2D map and a laser rangefinder, yes, we can really do very well. But there's always a way to make it harder. And once we start to pick up a camera and want to try and move it really rapidly in really varied lighting conditions, with varied sorts of scene, with low computer power to make it realistic, then I think there's still a lot of theoretical challenges there that are very interesting.
Okay, I'm sorry to say that we have to stop here. Let's thank Andy again.